All right, last couple of times we talked about how the network stack is a system software that's really common today. Today I want to talk about assemblers, compilers, and linkers as system software. This was one of the big developments in system software, and it's been a long time ago that this was developed, so it's really common today. This comes basically from Chapter 8 in the book. It'd be nice if you read Chapter 8. The basic system software is to build something that's the basic concept. Build something that is farther away from assembly language and is easier for us human beings to interact with and use, and easier to get software implemented correctly in, and easier to test. Lots of research in this area is ongoing. Companies like IOHK, which is now a Wyoming company, are developing domain-specific languages like Marlow for financial technology. And if this is something that interests somebody, this is the kind of a field that if you go on to a master's, building a domain-specific language is actually a decent research project for a master's. So we're going to take a little bit of look at some things along those lines. But first, let's talk about how assemblers actually work. And you've been using one in this class. And there's one built into the microcode emulator as well. So how do they work? Almost universally, assemblers are two-pass systems. That means they're going to go through the code once, do some work, and then they're going to go back to the beginning and they're going to go through it a second time. So during the first pass, let's say we take this little program that's got a load, a store, a halt, and declares two locations, X and Y, for storage. So we're going to start out at a PC of 0. Now this is not running the code, this is writing out the assembly instructions. But we're going to start out at location 0 at the beginning of our little piece of code. And so you fake generate a load instruction. This means that you calculate out the amount of storage that a load instruction would take so that you can increment the PC appropriately. Lots of hardware has instructions that take more than one location. Our little system just takes one. So we're going to increment the PC to 1. And we're going to fake generate store instruction. We're going to increment the PC to 2. Now the purpose of this first pass is just to calculate the labels, so we don't have to actually generate anything. What we want to do is figure out where X and Y are. So we go on to the halt instruction, and we fake increment to 3. Fake generate increment to 3. And at X comma decimal 10, we read the label X, we say, oh, we've got a label. So we're building a list of where these labels are, and the PC is currently 3, so we're going to store that location 3 associated with X, and it's a decimal, so we're going to increment one location because we're going to store one number there, but we don't actually generate the number. We just note that X is at location 3, and we go on to the next one, and we see then that Y is at location 4, so we're going to do the same thing again for Y. We're going to associate it with location 4, and we come to the end of our file, which means now we want to go back to the beginning. Now, a long time ago when these were tapes, this literally rewound the tape, but these days, usually when you build an assembler, you don't actually go back to the beginning. You have all of the code in memory, and you just start over in your list of lines in memory. So in pass 2, for the same code, we start at the top, but we've already got the addresses of X and Y at 3 and 4. So we come to a load instruction at the top of the program. We load, but we know that we're going to generate a 0x1000 instruction. But now we know that X, the hand, is 3. So we put those together and we get 0x1003. And we generate that. A store instruction is a 0x2000. 2000 hex, and it's storing in Y, so we know the address of Y from the first pass is 4, so we're going to generate 2004 hex. The halt instruction is just a straight 7000. The generate for the decimal 10 is a 00A instruction. And the generate for the decimal zero is a bunch of zeros, and we're done. So that gives us our little tiny program. And that's the way that assemblers work. Now, there are some other things that assemblers sometimes do in more complicated systems. We'll talk about that with linkers and when we do compilers. But this is one of the first things that people built as what I would call system software. Originally, assembly language programs, if you look back at the history of all this, they had assembly language coding forms, and you would actually see where the person would write down the code with a pencil on a piece of paper, and there was a second column for the person to hand assemble the code into the binary instructions. And they automated this process with a piece of software. Yay, I'm not that fond of hand assembling code. And that made our first system software. So how do compilers work? Compilers took a lot longer to build. They have lots of fun parts. And, if you had to look at something that in the land of computer software is one of those things that uses everything we do in computer science, I think you'd look at compilers. There's just that many fun parts. The original compiler, Fortran, is built on a circuit board, literally that was covered with diodes, where the diodes, if they were there, represented a 1, and if they were gone, they represented a 0. I think that's how those boards work. It might be flip-flop from that. But the 1s and 0s in the actual program were created by cutting diodes out of the board with a pair of wire cutters. Thinking about it, I bet the people who developed it, like Dijkstra, actually got blisters from programming, if you can imagine that. So Fortran is still around. I've used it in the past week. It's hard to find Fortran programmers these days, so us old folks that have programmed for a long time occasionally get called in to do work. And specifically, I made some fixes to some genetic analysis code that looks for mutations in COVID-19. So it's still used in lots of applications, things like the Hadron supercompiler. The control system for it is all written in Fortran. The big developments in compilers involved parse trees and language specification. We're going to look at some of those things here in a minute. Compilers today are super reliable. I mean, it's just amazing what the quality of the software inside compilers is today. And a lot of that has to do with automated testing and the ability to determine that, yes, this is the correct solution for any particular kind of input. When I first started programming, I remember the question was always, if you looked at a piece of code and it was broken, was it the code that you wrote was broken, or the compiler didn't generate the correct assembly code? And also, the quality of compilers in terms of what it gives as feedback to the user is much better than it used to be. I worked on a program in Fortran 66, and if you had a syntax error in this almost 4,000 line piece of code, down at the bottom, it printed out the word syntax error. It didn't even tell you what line your syntax error was on. It just gave you the word syntax error. That was it. So when I see some sort of software development system that does that today, I pretty much roll my eyeballs and go, ugh, can't they make any progress in all these years? But there are still some out there that are that bad at reporting errors.